Okay, welcome everyone. This is the weekly webinar sponsored by CDAC, the Chicago DOE Alliance Center here at UIC. Today, I'm very pleased to introduce one of our colleagues, Miao from Cal State Northridge. Miao is trained as a theoretical chemist and is now working on a variety of problems in high pressure. He received his bachelor's and PhD degrees from Gillen University, which is an institution that's trained a number of people over the years in the field of high pressure. It's a very impressive track record, and they're now around the world. After a postdoc at Case Western, Washington State, and UC Santa Barbara, Miao moved to Cal State Northridge in 2013 as a research professor in physics, and moved up through the ranks, and most recently was appointed associate professor in the Department of Chemistry and Biochemistry. Miao has been quite prolific over the years, exploring, as you can see here, novel chemistry under pressure, and exploring the implications of that chemistry to a variety of problems, from new materials to earth science. So welcome, Miao. We're looking forward to your talk.
Okay, well, thanks, Russ. Thanks for the introduction, and especially thanks for inviting me here. I found this CDAC a very, very active community, and there's so many wonderful talks in the past weeks, and I'm very happy to make a contribution. So the title is fairly broad. So here is an outline. Okay. Oh. So most of the stuff that I'm going to talk about today can be found in this paper. It's very recently been published in Nature Reviews Chemistry, also with a very broad title, Chemistry under High Pressure. It's co-authored by me, Yuanhui Sun, which is a postdoc in my group, and Eva, we all know Eva, and Professor Lin in China. Okay, so here's an outline. So basically, I will just briefly introduce a little bit about the background, and I will focus quite a bit on the theory. So especially, I mean, recently we have so many new compounds has been predicted. Many of them have been synthesized. So how should we view them? Why they exist under high pressure, right? Especially, they are compounds with very atypical composition. And then we'll focus, well, first I will briefly go through the chemistry caused by the change of chemical bonds under pressure. And then we'll focus more about the chemistry caused by the change of local orbitals. And these local orbitals include the core orbitals, so that because of the change of the core orbitals, that the core electrons will evolve in chemical reaction. And then the outer orbitals, right? The orbitals that supposedly not occupied by any electron. And even more interesting and weird is that the non-atomic orbitals under pressure can start to take electrons, and then will completely change the property, the composition of the material. A little bit about the reverse chemistry of iron. It's still ongoing. The paper hasn't been published. So on. If we have time, I'll talk about the chemistry with no chemical bond, which I think is very fascinating, although not too many materials will show that property. Okay, so matters under high pressure, and we are all very familiar with that. What I want to emphasize that in the past, the whole community are more focused on the topics like structure change, polymerization, the physical property changes, right? There are so many different physical property changes under high pressure, like metal insulator transition, new superconductivity material, or even topological insulator, magnetic properties, so many. And the reason that the whole community have been focused more on those is because those phenomena will happen under lower pressure, right? And while the pressure, the DAC experiments and some other shock experiments reaches a lot higher pressure, now we enter to a new, new time. In this, the focus now is more like the new compounds. is the compounds that does not even exist under low pressure, right? So here are several examples, right? They cannot be synthesized. They can only be synthesized under high pressure, and many more of that. And another, a very important trend is in this new area, the computation plays very important role, right? And sometimes I call it a riot of the computation, a coup of computation, because in the past, well, this is really due to the development of computation power, especially the computer, and partially due to the development of the method too, which is also very important. If you look at this development of the computing power, right? So this Moore's law, it doubles almost every 18 months and so on. It has been going on for like many decades, right? So one important trend is that, of course, the size of the system that we can calculate becomes larger and larger, right? We can calculate, water molecule has already been achievement many years ago, and then larger molecule, and now the biology, molecules and the solids also, right? So we can calculate the bulk of materials, and then the defects, and then the dislocation, and so on. So the system we can study becomes larger and larger. But there's another important trend, is that not only we can calculate larger and larger system, but also we can study many structures at the same time. So that gives us a power, right? It's a power of prediction. So this is like, DFT method combines with one type of, crystal prediction method, what we call the particle swarm optimization. There are many other, methods out there. This is just the one that I have been using more often. So by combining these two, we can predict the structure from basically no chemistry input, right? As far as we can imagine, we can put two elements, a few elements together. We assume that they might form compounds, but we do not know the structure, and we can predict the structure, right? If we can do that systematically, then we gain another, power. This is from calculation now to prediction, but more, the next step is the exploration. So basically, if you take our ternary compound phase diagram, right, you can, in principle, the computing, demand is very large, but in principle, you can predict at any point with an arbitrary composition, right? You can predict the most stable structure of it. And once you can do that, you can construct a phase diagram, and then you can show whether our compound can be stable or not, thermodynamically stable or not. But of course, it doesn't mean that it does not exist if it is not thermodynamically stable, and so on. But there's another issues. But whatsoever, this computation gives us a power to explore, right? So, before, as a theoretician, very often we need to wait till the experiments provides us a structure that we can set out to do calculations, right? Otherwise, we can, the wild guess, very often is not good enough, right? Okay, so with this power, there's many compounds has been predicted. So here is our set. This is just a small fraction. This is figure 1 in our paper. Is constructed by Yuan Hui. So this is just a small fraction, and there's another set. This is figure 2 of our paper, and this, as I said, is only a very small fraction. So the next thing is, although we can run the calculation is still very expensive, and especially if you notice that all the previous compounds that we have studied, they're binaries. And when the community want to move ahead and study ternary and quaternary compounds, we have another problem, because the prediction of the structures for quaternary and even ternary compounds becomes extremely more expensive, right? So we need some understanding why these compounds can become thermodynamically stable under high pressure, right? So this is one of the major tasks. of this talk. So grouping the noble compounds. I want to bring ahead these two different compounds that have been predicted almost at the same time. One is sodium chloride, and the other is cesium fluoride compounds. And these are the phase diagram, or the convex hull of them. So if you look at sodium chloride under high enough pressure, right? For example, above 20 GPa, this is 160 GPa, and it's already become stable. It can form sodium trichloride, for example, and some other composition too. If you look at cesium fluoride, so this is cesium fluoride 1:1, and this is fluorine. And you can see under pressure that is higher than 30 GPa, and this is 50 GPa, this cesium trifluoride also becomes stable. So it can form cesium trifluoride. But are these two compounds the same group? Should we put them in the same group? They are both atypical compounds, meaning that they are compounds with atypical composition, right? The typical composition for sodium chloride is 1:1, right? It's a table salt. And for cesium fluoride is also 1:1, right? So this cesium trifluoride, cesium trichloride, they are both compounds with atypical composition. But are they the same kind? If you look at the structure, they are very different. If you look at the sodium, the sodium trichloride, you can see that the reason that it goes beyond the typical composition is because that they form chlorine and chlorine, they get together and they start to form bonds. Okay, so the reason it goes beyond the typical stoichiometry is because the anions, they form bonds. But if you look at the cesium trifluoride, that's not the case. The anion, the fluorine, they do not form bonds. Under very low pressure, they do. But under higher enough pressure, they don't. The reason it goes beyond the typical the typical composition is because cesium forms bonds with more than one fluorine, right? So you can see that here the cesium forms two covalent bonds with the fluorine, and you have an isolated fluorine atom that is an anion. So although these two has the same stoichiometry, they're very different compounds. So what happened? So here is a way to understand it. So first we look at the compounds under 1 atmosphere, right? The normal pressure. Under normal pressure, with many years of inorganic chemistry development, we know that elements often assume a typical oxidation state. Some elements, especially the transition metals, for example, they can assume, two or few oxidation states. But for most of the elements, they assume one typical oxidation state, especially, right, if you talk about alkali metals, they're +1, alkaline metals, they're +2. The light, oxidant elements like fluorine always -1, oxygen very often -2, right? So those are typical oxidation states. Well, there are many exceptions. I use the small letters here, showing here. Also, another very important trend is the heteronuclear bonds tend to be stronger than homonuclear bonds. Well, again, this is a very broad statement, and there are so many exceptions. It really strongly depends on elements. But for light elements, for strong oxidant elements, they tends to be true, right? And the reason is fairly simple, because you have a homonuclear, you have two atoms, the same atoms, they form bonds together, they form the homonuclear bonds together, the splitting of the bonding and anti-bonding states that determine the strength of the bond, right? But if you have a heteronuclear, you have one nuclear has a higher energy, orbital energy than the orbital energy of the other one, the electron will transfer and release a great amount of energy. And especially if, B is our strong oxidant element, right? And A is alkali or alkaline metals, then this energy transfer is very large. So therefore, they can have a much larger, heteronuclear bonds. And because of that, the compounds will tend to form a typical composition, meaning that they have, a fixed oxidation number, and also the anion will always, the cation always bound or surrounded by the anions, anion always bonded or surrounded by cations, right? So, and again, I would like to emphasize here with the small letters, this is the commercial flyers that you receive, like satellite TV or internet cable, commercial flyers, right? They have $39.99 per month, the cost, right? But they have small letters there, right? Be careful, you need to read the small letters. After 6 or 12 months, it goes up to $79.99 per month, right? So that's, but I think the major trend is there. The major trend is there. So what will happen under pressure? If we put pressure on that, well, this energy splitting can be understood by a simple Huckel model, right? So here's the simple Huckel model. Alpha A and alpha B and beta is the resonant integral, or in solid state physics is the transfer matrix element. It's like the T of the TJ model. It shows you the how strong the transferation from one from one orbital, from one atom to another atom. Okay, so this is the integral. Okay, and if you solve this, you get the energy difference between the bonding state and anti-bonding state is this much. Very simple and straightforward formula. And now, if we want to see what is the effect of pressure? If we apply pressure, then alpha A and alpha B and beta, they will all change, right? It is hard, and of course, the relative change, the relative shift between A and B is more important. Well, there's no general trend for that. We cannot say that alpha A minus alpha B always goes up or always goes down. It really depends on the elements, right? Depends on the orbital. Some orbital is more sensitive to the pressure, some is less. So it's really hard to see the direction of alpha A minus alpha B. However, beta usually goes up. It usually goes up because under pressure, most of the bonds become shorter, right? Become shorter. Well, there are some exceptions, but those exceptions are actually not within our consideration. For example, hydrogen atom, if it forms hydrogen molecular crystal, the hydrogen bond length actually goes up a little bit in certain pressure range. If you increase the pressure in that range, it goes up a little bit. But that's not the case that we're interested. We're interested at the anionic, molecular groups, right? For example, the chlorine form bonds, and there's a charge on that, and if you increase the pressure, the distance between the chlorine atoms will go down, and therefore the beta will go up. So how does the bond energy, this EB, the energy difference between the bonding and anti-bonding state, change with this beta? Well, we can do this very straightforward, first order derivative calculation, and we get this formula. So delta EB is proportional to delta beta in this way, right? And we can see the two extreme cases. One extreme case is the homonuclear. It's alpha A equals to alpha B. If alpha equals to alpha B, then the first term here will disappear. Then delta EB is simply 2 delta beta, 2 delta beta. If we consider our very strongly polarized bond, the alpha A, for example, is much higher than alpha B. Alpha A is much higher than alpha B. Then the first term dominate, and we can neglect the second term. So what's happening? Okay. Am I still connected? Okay.
Yeah, you're still connected.
Okay, good. Thank you. Yeah, it's my computer. All right. So so alpha A will be much, well, in this case, alpha A is much larger than alpha B. And then we can neglect the second term, and then delta EB becomes 4 beta divided by alpha A minus alpha B and delta beta. And we know that alpha A minus alpha B is much larger number than delta beta, because we assume it's a polar case, right? And that is the reason we neglect for beta squared. And then therefore this should be much smaller than 2 delta beta. So this shows us that the polar, very, very strongly polared bonds is insensitive. It's not as sensitive as the homonuclear bonds. So homonuclear, the high pressure will increase the bonding energy for homonuclear bonds more. So if we see that see that trend in this figure, we can see in the first case, the bonding energy will increases a lot. And the second case, for heteronuclear bonds, it will also increase, but not as significant as homonuclear bond. And there are other trends, of course. First, alpha A and alpha B will change relatively, right? So the direction can be both way, And some other important, trend is this levels, right? So for example, this is a core level. Usually they do not involve, they may have effects, but they do not directly involve in forming chemical bonds, right? Because down below there. But if you increase the pressure, and if this core level, goes up a lot more than alpha beta, then to a certain point, they can form bonds with the neighboring anion atoms, right? And anionic atoms. Or you have the lowest unoccupied atomic orbitals. Why it is atomic orbital, it does not occupy, and also usually it does not occupy. Why they form compounds? Because they are too high in energy. But if relatively, well, all the orbitals will go up. So this arrow only shows the relative shift, right? If relatively this alpha A goes up and this LUAO goes down, and then to a certain point, they can accept election, and then they form bonds, right? So therefore, we can categorize our atypical compounds, or compounds with atypical composition, to two different kinds. One is caused by the change of the chemical bond under pressure. So basically, pressure can enhance more the homonuclear or less polar bonds. But more interestingly, although the examples that we have are much less in the first kind, is that the pressure alters the energy, or energy orders especially, of the local orbitals. And we have several examples, and I will talk more about those. Okay, so novel compounds form due to the change of chemical bonds under pressure. And there's many of them. I show this picture again. So especially I would like to emphasize that, the anions, they form all different kinds of new species. And so this, for example, this is the N6 ring that Rode mentioned last time, I believe. And also, of course, this. And as Rode mentioned, very often that this new species, this quote unquote new species, can already be seen in the compounds under low pressure, right? Under ambient condition. So then what's the achievement of high pressure then? Here is the things that I summarize, and I think we can consider that's the achievement of high pressure. Well, first, it does include many new homonuclear species that you cannot see, under ambient condition, right? And also sometimes, although you can see, but it's different elements. And as this Prevedon, I think they have 10 rules of compounds, and those rules are summarized why they study structure change. But some of the rules still apply for new chemistry for novel compounds, right? Atypical compounds. For example, one is that the element will behave like under high pressure. An element will behave very much like the element that is below it in the periodic table, right? So yes, indeed, you can see, for example, the same structure, that complicated structure or motif that is formed under high pressure, the same one that you can find in the ambient condition, but they are for different elements. They're for different elements. And the reason for that, again, is because the homonuclear bonds become, are enhanced, right? Are enhanced. So that is the first effect of pressure. The other thing is the formation of the homonuclear species can be found in one type of compounds, right? So for example, the nitrogen species. Yes, indeed, you can find, many, nitrogen species, polynitrogen, polynitric species at the ambient condition, but they are from very different compounds, right? Magnesium or manganese, iron, all this. But for high pressure, what we can often find is that all these different types of species can be found in one type of compounds, right? For example, magnesium nitride, right? With various composition, and then you can see all different kinds of species in all this one. And more amazing is the third one, is all these different homonuclear species can even be found in the structure evolution of one compound, right? I have a typical example is this carbon, and this is yttrium carbide, and calcium. I think calcium carbide has also been very well studied. So it's just one single compound, the structural evolution of one single compound, no change of the composition. And while you keep compressing it, you form more and more, this carbon species with larger and larger size. Eventually it becomes, the intercalate of the cations into this graphene layers, right? So it's very extended carbon species. So that's another thing I think that the pressure can offer to us, and this is really interesting and exciting to explore as high pressure scientists. Okay, so new compounds formed due to the change of local orbitals under pressure. The first example I like to give is the reactivity of core electrons. I will, I'll probably just go very quickly. It's more like our snapshots of several cases. I'm not going to spend much time on each single of them. I think what I find interesting is why you put them together, right? All this, cases, you put them together, you can see a very general trend of matter under high pressure. So this case is the core electrons. Well, here's a periodic table, and we know the chemical property, or sometimes I say the chemical identity of an element, strongly depends on its position in the periodic table. And we also learn that, for the elements, locate at the left side, it tends to lose electron, and for the elements locate at the right side, especially in the upper left side, it tends to gain electron. But this is like a wall. So once you hit that wall, it means that you lose electron or gain electron, and then you have a complete shell, right? And then you stop there. So that's what we learn from the ambient, the chemistry on the ambient condition. But with the new computation tools that give us the exploration power, right? So we can ask the question, under high pressure, can we break that, that wall, that boundary? And the first example that we tried is this cesium fluoride compounds. So indeed, we find that the cesium can form, atypical, the compounds with atypical composition, like cesium trifluoride. Cesium difluoride, it has a very narrow range of pressure that they are stable. And I cannot guarantee that they are not the artifact of computational method. But cesium trifluoride, it has, a large pressure range that they are stable, and it becomes the formation energy becomes lower and lower with increasing pressure, right? So although many people will ask the question of whether the exchange correlation functional is good enough or so, whether it can predict it, I can say that because of this, that the formation energy becomes lower and lower, that means that cesium trifluoride becomes more and more stable under high pressure. So it does have a driving force there. So maybe the predicted transition pressure is not accurate enough. Maybe it's not 30 GPa, maybe it's at 50 GPa, but definitely cesium trifluoride can form. And also cesium pentafluoride can also form. Not only that they form these atypical compounds, but also their structure shows that they can, they form is because, it's not because fluorine and fluorine form bonds, right? So that satisfies the composition in one way, right? But the reason that it can go beyond 1-to-1 ratio is because cesium form more bonds with fluorine. And the reason cesium can form more bonds is because the inner core electron, it has been squeezed out and react, right? So here is the beta charge that we calculate. You can see that it increased steadily with the increasing number of fluorine in the system. So that's one evidence, and there are many other evidences. The geometry itself is a good evidence already. And the ELF, what we call the electron localization function, that shows you the bonds, the formation of the bonds. Well, it shows the electron localization, but it indicates the formation of covalent bonds between the neighboring atoms. So for example, here, it has a fairly strong value. It's as strong as xenofluorine bonds, right? So so definitely it forms a covalent bonds, between fluorine and cesium, and it forms a molecule. This molecule is isoelectronic because it's +1 charge. One electron has been transferred to the isolated fluorine, and it's CSF2+, and it's isoelectronic to xenon difluoride. This one is amazing, and it's really come out from computer, right? I cannot imagine this cesium pentafluoride starfish-like molecule. But this is another proof of what Rode emphasized last time. Whenever you find a new structure, you're advised to go back and check, what people have seen before. So while I see this first, I thought this definitely something new, right? There's no way they have been found. But while I settle down and write a paper and check the literature, I find not only people know that, they have already synthesized that. This is for xenon pentafluoride, right? That's our negatively charged molecule, and it has been synthesized in solid. It's exactly the same structure, and that's because they are isoelectronic. So that's this. Okay, the reactivity of outer orbitals, I'm not going to go details of that. I'm just going to say, to tell you that under pressure, the one example is that the noble gas can form compounds with, alkali or alkaline metals. So this is one of the work, and there are other couple of works. You can see those in my in our review article. So that's definitely, the reason that xenon can form compounds with magnesium is because there's a charge transfer from magnesium to xenon, and xenon can accept those electrons is because the xenon 5d orbitals become low enough in energy. Well, not really low, but relatively. I mean, all the orbital energy will increase, but they just do not increase as fast as the magnesium 3s and 3p orbitals. So the electron will start transfer and occupy xenon 5d orbitals. So that is the reason it can form. Here's another example. If you put lithium and cesium together and form compounds, People have already started. I missed the literature. That was a mistake. I didn't see that while I write my tape, my paper. People have already seen that. However, their study, and they're from semiconductor community, their study is focused on low pressure range. On the lower pressure range, like below 10 GPa, 20 GPa, lithium cesium formed compounds, the cesium electron transfer to lithium, and that's reasonable, right? Because cesium has lower ionization energy, right? So the electron actually transfer the other way. But if you compress it high enough, it goes up to 100 GPa, 150 GPa, the charge transfer goes totally different direction. So now cesium becomes negatively charged, right? Because charge transfer from lithium to cesium. And the reason for that is because the cesium, again, very similar to xenon, is because the cesium 5d orbital becomes lower in energy. So it can form lithium ceside, and the beta charge, if you calculate, it can go up to 2 already. So that means that cesium can go beyond -1. Cesium -1 has been seen under ambient condition, but this one can go beyond that, cesium -2 or -3, like that. Okay, this is a good example, and I like it, but I assume it's many of you have already known it well. So basically, well, here's something I like to emphasize. I always start this story from the work published in 2009. One is from Yan Ming's group, and well, sorry, it's not Yan Ming's. It's Yan Ming's the first author, and collaborated with like Organov and Miao group, who did the experiments. And also there's a Japanese group did similar experiments for lithium. And they found that the lithium and sodium can develop a gap, and sodium becomes an insulator. Lithium becomes our narrow gap semiconductor, which behave very different to sodium. But the high pressure electride story goes way back to that, and indeed this is also what I think Rode emphasized. People have a lot of wonderful work that hopefully that we can recognize all those. It's just not so easy. So for example, this electride thing, why we wrote this review article, we check everything carefully, and it always goes back to like 80s. So the first name, this high pressure electride, was actually dubbed by Schnering and Nesper in '87 in an Anguada paper. So it's really unbelievable, and that's for cesium. And then there are many other works, theoretical, computation, and so on. So I think we have done a thorough work, but still maybe we missed something. It's searching the literature and finding all the contributions. It's a very, very difficult task. And then people also predicted several other metals. For example, aluminum was predicted to become electride under extremely high pressure. Magnesium, 800 GPa. And if you go to really high, even carbon can become that. So what is the mechanism of forming HPE? And there are already, many explanations, like the transfer of the electron from S to P and D orbitals, or multi-center bond orbitals. So in principle, these are all correct. And I'm going to explain slightly later the relation. So here's what we propose. Me and Rode. So we basically say that if we introduce just one extra local orbital, and this extra local orbital locate at the interstitial site between the atoms, right? If we introduce that, and this quantum orbital can occupy electrons. Under ambient condition, this orbital energy is higher than the atomic orbital energies, right? The valence orbital energies. And the reason is simple, because you do not have a positively charged nuclei at the center to attract the electrons, right? But if you increase the pressure, right, then, okay, I don't have that figure here, but if you increase the pressure, then this orbital energy, all the local orbital energy will increase. However, the atomic orbital energy, or many of the atomic orbital energy, will increase faster than this, what we call the quasi-atom orbital energy, right? And then under certain high enough pressure, the electron will prefer to transfer from the atomic orbital into this local, non-atomic orbital, right? And that's the basic idea. And I think, as I said, there are many other explanations. So basically, if you have a DFT calculation, you find the crystal orbitals, right, at each k points. You can always, expand that to local orbitals, and any expansion is correct, right? So what I like this way is that it has a prediction power, right? First, it's very simple, and second, it has some kind of prediction power. It tells us, which orbital will cross this line earlier, under lower pressure, which orbital, although it has the same trend, but can only cross that line and become higher in energy than the quasi-orbital, quasi-atom orbital at much higher pressure. It can tell us that. And thirdly, I think more interesting is that with this, you can see something that's not easy to see. And this is an example. So why we assume that this is the formation of the electride is due to the occupation of these local orbitals, then we can kind of imagine this local orbital is like a chemical species. They should have, they should have the properties like an element. They can, for example, they should be able to form chemical bonds, right? And we propose that idea purely theoretically in the Jack's paper, me and wrote. But we didn't expect to see that in real material soon. But then later on, we realized the example of the real material is right next to us. This is in a paper that we we collaborated with a few people, including Russ. Is that how to explain the same phenomena in lithium? Lithium and sodium is very different. In lithium, as I said at the beginning, the gap in lithium is much smaller. It's only 0.3 eV. It's a narrow gap semiconductor. And if you calculate the charge distribution, and in some of the interstitial sites, if you count the number of charges, it's more close to 1 than close to 2. That means in some of the local orbitals, it is singly occupied. If you have singly occupied orbitals, then it should be metal. So why it is not a metal, but a semiconductor, right? So by doing careful calculation, we find that for those singly occupied orbitals, they're always next to each other, and they actually form chemical bonds. And because they form chemical bonds, they split and they occupy, the bonding states are fully occupied and anti-bonding states are empty. And that is the reason that it has a gap. And that is why that gap is much smaller than sodium, because sodium is purely an ionic compound in the sense that each local orbital, the quasi-atom orbital, are occupied by 2 electrons, right? So that's the major difference between this and that. Okay, and then we run the calculator, and we actually see the wave function showing the bonding state of lithium and the anti-bonding states. That's completely empty. The bonding states are totally occupied, and this is the co-op of that, showing that this bonding and anti-bonding states again. Okay, I'm not going to emphasize this. Do I have? Is the time already, Russ?
No, keep going. It's fine.
Okay, I just use few minutes to explain this idea, and then I will skip the other one so that I can save some time for questions. So this is a new example. Well, it's my fault probably. It's we haven't started studying this system for a few years, but you know, it's not published yet. So basically, we use the same method, but we studied almost all the p-block elements, the reactivity of p-block elements. And I'm sorry if you know, the font is too small, but this is one period. This is boron, carbon, you know, nitrogen, oxygen, fluorine. And then, you know, so these are the p-block elements, and how do they react with iron? There's one trend that we find is very interesting. So very often, if iron form already very strong bonds with an element, for example, with oxygen, right? Then its formation energy does not change much under pressure, under increasing pressure. But if an iron that forms relatively weak bonds, right? Very weak bonds. For example, this one. So this is germanium. This is arsenic, right? This is arsenic, selenium. They form weak bonds under ambient condition. But if you increase pressure, you find that the bonds, the formation energy becomes, you know, formation energy becomes lower and lower. The bonds become stronger and stronger, right? So this iron forms, you know, more and more stable compounds with elements like that. So what causes that, right? So this is something that you know, has been predicted, has been seen in another work. That's Yanming's group. Yanming and Chris Picard, they studied the iron react with xenon, and they found that iron, under very high pressure, that iron can react with xenon. Under low pressure, it does not. Under very high pressure, it can. And while it reacts with xenon, iron plays the role of oxidant. It actually oxidizes the xenon, right? So what we study here is that we carry this and then we go further, and we find that for many elements, it has this reverse effect. So under low pressure, well, this figure is a little bit complex, but you can see this is 0 GPa, and this is 150, this is 300, and this is the beta charge that we calculated. And this is for an element in one period, like carbon, nitrogen, oxygen, fluorine, right? And this is phosphorus, germanium, phosphorus, sulfur, and so on. So you can see that it shows the charge on iron. So you can see at 0 GPa, for most of the compounds that iron forms with the other elements, iron is positively charged. So for example, if you take iron and iodine, then it forms iron iodide, right? So it's iron iodide. But if you look at higher pressure, the charge transfer has actually been reversed, right? So at 150 GPa, the iron is slightly negatively charged comparing with iron. And if you go to 300 GPa, it's largely negatively charged. So you have this charge transfer reversal. So iron iodide now becomes iodine ferrite. So you can see that the chemistry is totally reversed. And because of this reverse chemistry, the formation energy becomes lower and lower. So because under high pressure, this reversal becomes stronger and stronger. Iron will become a stronger and stronger oxidant, right? And then it can form stronger and stronger bonds with the p-block elements. And because of that, you know, you can see this general trend that the compounds becomes, you know, iron forms, you know, stronger and stronger bonds and more and more stable compounds with this late p-block elements. On the other hand, it's bonding with elements like carbon. That's very, very obvious, very distinguished. Oxygen to nitrogen, they do not change much. And that is because, it's not reversed, but iron becomes less and less a good reductant, right? So it's becomes more and more resistive to lose election on the high enough pressure. So we try to use this to explain the incorporation of these elements into the core, to explain what happened, what people call the element, the trace element missing in geoscience. But to our surprise, what we find, while we put everything together, what we find is the opposite. Basically, it shows that this chemistry does not explain. Basically, it shows that it does not explain. It basically shows the incorporation of these elements does not seem to be the reason that these elements are missing in the silicate, what we call the silicate Earth. Is the or geoscientists called the Earth scientists called the silicate Earth, is the lower and upper mantle. So because the trend is totally the opposite, it's totally the opposite. That the stronger bond between iron and the element does not go with the missing of it. It's the opposite trend. So that's what we show here. Another interesting thing is if you put several major elements together here, so this is iron and silicon, and this is iron and oxygen, and if you see the formation energy per bond, change with pressure, then we can see that silicon behaves very, very different to other elements. It goes down much quicker and forms very strong bonds with iron under the condition of core, pressure and well, we didn't include temperature effect in this study because it's huge. It's a very large scale research. We have done the structure search for all different kinds of compositions for 23 elements. So it's a huge, large scale study. However, I think what we review here is the bond strength. It doesn't really matter whether it's a liquid state or solid state, although our calculations are on the solid state, but we believe that the bond strength change, the trend of the bond strength change should apply to all kinds of states. All right, so that's this. I think I will skip this part. The chemistry with no chemical bonds. Basically, we propose a mechanism to explain the helium insertion into several compounds. So including sodium, why sodium can form stable compounds with helium, and that's because sodium is not sodium anymore under that pressure. It's sodium 2 E, and E is the empty site, or the ISQ in our words, the quasi-atom. So it's like an A to B ionic compounds. So we kind of say that the helium insertion has a mechanism because it relieves the strong repulsive interaction between the same type of ions. Why you do not have this helium? They get too close and they have strong repulsion between each other. And why you insert helium, you can relieve that energy. But this type of mechanism, it's different to the two types that we have discussed today, the change of the chemical bond or the change of the local orbitals. Here is purely long-range interaction, and it's very subtle. We tried different compounds. It works more distinguishedly for hardcore ions, right? So the ions is less polarized. The outer shell orbitals are too high in energy, right? So for example, lithium ion, fluorine ion, magnesium ion, oxygen ion, they work very nicely with that. But if you use our polarizable ions, cesium, for example, or some others, it has complications. So that is one. And second, although we say here the insertion into an AB type is impossible. Well, it's not impossible. It will increase the energy, right? It actually does happen. And in our recent work, we do show that helium can be inserted into sodium chloride, for example. And that's totally because of different mechanism. And we have worked that out, and we're writing paper on that. Okay, I think that's, yeah, okay, I'm not going to show this anymore. So again, I emphasize that this is the paper, and most of the topic today, you can find it there. The paper, I think, is written in, we tried our best to give, even details in many aspects. And we try to write it so it's more interesting to students, undergrad students, seniors, or first grade, second grade graduate students. They just enter the field. We try to make it interesting so that they can be attracted. So if this might be a good entry level article for the students who just started their work, or they are looking for a direction to go. I mean, if we can use that, students who work in our field, that would be very wonderful. So here's acknowledgement. So here are the people that we have been working together. Many of them have already, found positions. Xiaoli is working right now in Yantai University as a professor. Jorge got a position in South California. He's very happy with that. And Jen is now working Beijing Normal University. Yuan Hui is currently working with me as a postdoc supported by NSF grant. Lei has gone back to China. She's looking for a position. And these are the two students who have worked on a high pressure project at CSUN. And here are my collaborators, and it should be longer than that. I just put especially people who involved in the topics that I speak today. So many of them, we know them, we know them very well. There's one thing that I'm not happy about why I write down these collaborators, is they're all theoreticians. I hope that I can collaborate with the experiments. Ross is exception. That's simply because Ross has done both theory and experiments. And I would say, it's only the theoretical part, the theoretician part of Ross collaborated with us. So I hope that in the future we can collaborate with the experimental experiments, part of Ross. Okay, so that's the acknowledgement for funding. NSF career, I am really thankful that that gives me a lot of more time focusing on research. And ACS PRF, that's all the junior faculties want to get, to get, and some other internal fundings that also give like teaching release time, which is also very helpful. So thank you for listening, and I'm ready for question.
Thank you very much, Miao for covering so much, all the different classes of bonding in these materials under pressure. I couldn't help but think during your discussion of all the bonding that's developing between iron and the different elements that Francis Birch must be smiling down from heaven, because he predicted back in 1952 in a joke almost that the iron core of the Earth is really iron plus a unspecified mixture of the rest of the periodic table. So that's very interesting. Anyway, I'm sure there are questions. People are staying on. Please just unmute yourself and ask, or put it in the chat.
I have a question. Wonderful talk. Thank you so much. This is Su-Xin Hu from University of Rochester. My question is about the idea of this local orbiter explanation of this high pressure induced electride. I thought that's a very intriguing. So my question is that when you consider the local orbiter, would that like centered at the middle of the interparticle distance, or I mean, basically, what's the center of that local orbit you refer to? I guess that's my question.
Yes, yes, it's really the point of this idea. So if you look at the metals under high pressure, people are puzzled, you know, is this. Under lower pressure, many of these metals are stable under the close packing structures like FCC or HCP. But under this high pressure, and suddenly it becomes an open structure, meaning that it has or interstitial side that has a very large radius, right? And to accommodate electron. And so that also gives us, you know, support the idea of introducing a local orbital, is that this local orbital actually centered on this interstitial side, and it's surrounded by, you know, in sodium, it's surrounded by sodium cations. And of course, we only we propose two, you know, different levels of models. One model is purely analytical, so by solving the quantum orbital, if you see the paper, by solving this with our infinite wall, spherical wall model, and so we can use that, but we completely neglect the surrounding sodium plus cations. But the surrounding, so as you mentioned, the surrounding sodium cations can indeed change the quantum, this local orbital energy. But you know, that effect is hard to include. But in another model that we, in another model, in helium matrix model that we model, it's also not included. So that is something that will have effect and that can be included. But you know, this is our kind of more like a thought model, and everything. If we do DFT calculation, all the effects should be there already. So
that's right.
Yeah. So I don't know whether we should. Maybe it is a good idea if somebody wants to invest some time in there to modify that model to include the surrounding ion to the you know, quantum orbital of this quasi atom. Yeah. Thanks for the question. I think it's very
Thank you.
Good.
More questions?
May I ask you a question? Regarding your new paper, which is in publication, you showed several view graphs with reactivity, and there was actually enthalpy of formation. Did you try to calculate a reaction barrier for predicted structures?
Yeah, that's a very good question. And I think the community, that's not our norm of the community. So right now you know, the prediction is still focused on predicting the thermodynamic stable structure and how that's relevant to the experiment. Well, of course, I mean the thermodynamic stable structure is always good to look for, but whether that can be synthesized with you know, precursor compounds that you put in diamond amber cell, and they should go through our certain reaction path. That is, I would say, method has been developing in that direction, but you know, most of them are still quite primitive, and the system we can study are much simpler. For example, silicon, or carbon, and for more complicated compounds, it's probably hard. Yeah, the barrier it's a challenge, and even for just reaction under other conditions. Sorry, even for for inorganic reaction in general, it's also a very tough topic. And also it's not necessary to be a bulk property. It's sometimes it's different phase, different state. Sometimes it's interface, it's diffusion. It's relate. There's just so many different processes related to that. I think the even computation, even with the development of the computing power, doubled every 18 months, I still don't see that will be a scenario that we can realize in the near future, meaning like 5 years. Is that?
Thank you.
Yeah, thank you.
Thanks. More questions?
This is Roald. Can you hear me?
Oh, yeah. Hi,
Yes.
Rose.
Hi, Mao Sheng. It's good to hear this work described. There's a lot of beautiful work. You may not see it well because I'm having computer troubles, but can you hear me?
I can hear you well.
Yes,
and I can see you well.
Good. Yeah. Okay. So the things that were useful for normal chemistry, or that helped Pruitt and people like him form certain rules of thumb for structures, were pretty simple things like electronegativity and ion sizes, for instance. And then there was the effect of pressure, which he knew so well. I think in time we will get these two under pressure, and I just wanted to mention two things. One is, I don't know if Martin Rahm is still on, but we have a paper on the changes in electronegativity in atoms, in single atoms under pressure. And Oganov has one in archive, but it's not published yet. Ours is in an obscure chemical journal, so the physicists will have to look for it. But there are things in there which are interesting and different, like a change in the electronegativity of the alkali metal atoms under pressure, a neon becoming the most electronegative element, and also a few other things like titanium and scandium, for instance, becoming the most electropositive elements under pressure. So, and there is interesting, I think eventually we'll get an ionic type, beginnings of an ionic type chemistry based on those, but now comes the next hesitation. And this is, I think on electronegativity, we have the beginnings of something. And I would urge people to look at the paper by Martin and Roberto Cami. We are not very good at propagandizing for this, but the work speaks for itself. On the size of atoms, the distinction between non-bonded atom radius, an ionic radius, and a covalent radius, which occupied the chemical community for a good part of the 20th century. That distinction, we have pieces of it. You have looked at it, and we have looked at it in various pieces. It's coming, but we don't have yet sorted out the fact that that distinction is about to vanish. That is, at some point as you compress, the distinction between the different kind of radii and the distinction between ionic and covalent bonding may not hold up as a useful device. It maybe it does. as you've shown in the beginning of your little model. But I have a feeling that just as the radii will begin to merge into each other as the pressure increases, so I think we will need something else to measure the size of atoms, or at least the irreducible core of the atom that cannot be compressed. But now, as you have shown, we can get electrons out of the core, out of what we thought was the core. And this is going, so I think it's an interesting time coming conceptually, but I think we're not there yet on atomic sizes. I think we have a beginning on electronegativity.
I totally agree, and I know that you have been leading our research, our exploration in that direction, and I'm happy that to some aspect, like this radius or atomic volume under pressure, that I'm also can be part of it. I will be happy to provide whatever we can, to help. Yeah, and I think many things indeed need to be rethought and redefined. So even for example, the atomic volume. So whether the atomic volume is more important or the ionic volume is more important, or something in between is more important. So these are all need to be thought over and even redefined under pressure. And I'm really glad that we have this community, and we're talking and we're collaborating. So hopefully that we can move this ahead under your leadership. Okay.
No, not mine, but yes.
Okay.
Just comment. Also, it's perhaps a matter of language and metric, because by saying there's a radius, you're assuming a sphere. And clearly your electronic structure calculations shows what look like atoms not being spherical. So
Yeah. That's true. That's true. Yeah. Sometimes we use some other way to define deduction of the volume, or some boundary, how to define the boundary between the atoms, and then redefine and then define that volume. That's the yeah.
okay. More questions?
Hi, Mao Sheng. Thanks for a really great talk.
Oh, hi. Good.
I am here, and I was just
Okay,
I really enjoyed it. And just to follow up there, it's really interesting to see when some of our intuitions fail and when they not. And with regards to electronegativity and radii and so on, they work wonders sometimes and they fail sometimes. And I thought about it when you showed the example of iron xenon, because there we predicted direct opposite, right? That iron will become more less electronegatively, drastically so, compared to xenon. Yet, what you see when you look at the bonded material is that it's de facto acting oxidizing. So that's a clear failure, you could say, of that concept, where in other cases it works as it should, so to speak. So it's
yeah, I mean, the difference
it's certainly
is
the beginning and not the end.
Yeah, I think it's a good thing, actually. There is something different and surprising. Maybe some new concept will come out from your point of view, and yeah, that'll be very interesting.
More comments or questions? Okay, if not, thank you very much. Wonderful talk, lots of compliments in the chat box. So,
Oh, I didn't see that. Okay, good. Thank you.
Okay,
All right.
We'll see you next week.
Okay.
Bye, Mao Sheng.
Okay,
Great
bye.
talk.
Bye, Rose. Okay.